As we jump into this warm-up problem, the first thing that you're going to do is what? What do we do every time? Thank you. We're going to write down our givens. And remember, you have that handy-dandy patented givens chart that we're going to write down. Do we remember this? We've been doing it. I know you do. I know you know it. We've got delta x, VIX, and AX. We've got delta y, VIY, AY, and the thing that holds it all together is time, right? All right, give me some givens. What do you know? Raise your hand if you've got something. Yeah, go for it, Ashley.
It's 36 meters from the building.
36 meters from the building. What is it? So where in that givens chart is that 36 going to go? The change in x. Yeah. So if we need it, let's draw ourselves a little picture here so we know what's going on. Okay, so there's our building. And the ball is going to be thrown horizontally like this. Not drawn to scale. I just like to draw really large parabolas. You're telling me that this is 36 meters. Okay. This one's a little bit different than the ones that you've done before. I wanted to throw this in there to make sure you really understand what you're doing and that it's not just rote memorization, right? So the 36, it says it lands 36 from the base of the building. That's your delta x. Thank you so much for that, Ashley. All right, I think I saw another hand over here. Is that true? Yeah, what do you have?
The acceleration to the y is -9.8.
Absolutely it is. Because we're on Earth, because we assume we're on Earth unless it tells us otherwise, right? Absolutely. All right, 2 down. What else can you tell me? Yeah.
The initial velocity of x is 22.2 meters per second.
Absolutely it is. The initial velocity in x is 22.2, 2, come on, meters per second. It says that it's thrown horizontally. So that means its initial velocity is only in this direction, okay? Which means that it's all in the x direction. Awesome. All right, we're making progress. We need a couple more givens. What else do you know? Go ahead.
The horizontal acceleration
Is, what'd you say?
0.
It is 0. Friends, we've been doing this for a little while now. I know that you and I have not been standing here face to face doing this, but we did this on Thursday. You spent all day on Friday working on this, right? You got to listen to me and see me working through problems. Hopefully you spent a little time with this over the weekend, okay? I want to remind you that these two are always going to be true. So when you're working on this problem in just a few moments, at least write this down. These are always going to be true. The question on the check-in problem is on Earth. So it's going to be -9.8. It's going to be 0. Okay? All right. Anything else that I know? I think there's one more thing that I know for sure.
VIY is 0.
VIY is 0. Yeah. How do you know that VIY is 0?
It's just gravity acting on it.
Yeah. Gravity is the only thing that's acting upon it, so it's going to be pulling it down. And at the beginning, this pink arrow shows you where its initial velocity is, right? Its initial velocity is only in the what direction? X. Only in the x direction, which means the velocity is 0 in the y direction. Okay? All right. So this one's a little bit different than the ones that we saw before, right? The ones we saw before, generally you filled in all of the y stuff to find time and then use that to solve for something in the x. It's the same principles, friends. This time we know everything in the in the x. We can use that to solve for y. Okay? So what equation are we going to use? The same one as always. What is it? Take a look. Find it on your equation sheet because you need to know where it is. Delta x is equal to VI in the x direction times time. Love it. Okay. Miss Carbling's favorite equation. It's there and it always will be. Yep. Anything go to 0 in this one? Yeah, what goes to 0?
1/2 acceleration.
No, you're exactly right.
T squared.
Yeah, that whole thing goes to 0. Why does it go to 0? Because the acceleration is 0. So we can get rid of that, right? And then we can solve this for time by dividing by Vx on both sides. Yeah. So you've got time is equal to delta x over Vx. If you're not doing this right now, you should be. And if you haven't plugged it into your calculator yet, you should. Please do this. Okay? Solve that for time. What do we get for a value? Anybody got something for me? 1.6? 1.6 what? Yeah, awesome. All right. So now we've got time. We've got the thing that pulls it all together. And now we can solve for delta y. Okay? I'm guessing you can do this. What equation are you going to use, friends? Same one. Do it. Right now. Go ahead and do it. I'm going to give you just a moment. Check with your table mates. Once you've got an answer, make sure that they agree with you. Ashley, what's up, honey? It is as long as you always right. Yeah. So I will tell you that, but don't go around spreading that rumor to let people get them. Start going. Start going crazy. We only use that blade. Because really, does that make sense?
You guys get your number?
Check with your table mates. Make sure that you agree. So delta y is equal to Vy t plus 1/2 AYT squared. That's going to go away. All right. Let's see. Natalie, did you guys get an answer? What did you get? Negative, what'd you say? 12.86. Do you guys agree? Yeah? Does everybody agree with that? Okay, because I didn't get that, but I want to double check and make sure I didn't make a mistake here. 1.6 squared times 9.8 times 0.5. Oh, yeah, okay. 12 point, what'd you get? 12.8? Okay. What does the negative mean? It's going down. So the question says, how tall is the building? So you could just say 12.8 meters, right? But if you put the negative in there, I'm not going to count it wrong because I feel like you did the physics. You know what I'm saying? Yeah. Questions for me right now? Are we okay? Okay. So what I need for you to do right now, friends, you're going to keep your calculator out. You're going to keep your pencil out. Everything else gets put away. I'll give you an equation sheet. I'll give you some problems. You need to move to your assessment seats. Please also, friends, please also take your computers with you. Okay? Take your Chromebook with you. And as you're moving back to your assigned seats, just a little of, I told you I was going to do it, so it's time that we needed to do it here. Oh my God, this is only.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah!
All right, so just a little vision there to help you give us a sense of what is going to happen today. So we are going to talk about vectors today, not the evil villains, but the mathematical relationship. Okay, so in your notes right now, friends, we are going to write down a few things and we're going to do a bunch of problems. That's our plan for the rest of the day. So if you don't have those notes out, get them out. If you did not take notes while you were watching that video, you know what? That's okay with me, but I want to make sure that you know what's going on. So you may need to go back and look back at it. The things that I need to make sure that you know, okay, is that a vector, we'll use orange to match them here. A vector is represented by an arrow. An arrow is really nice because it has both what and what? Direction and magnitude, right? So if I'm going to draw a vector, and you probably want to do this as well, it's going to look something like this. The direction is represented by where the arrow is pointing, and the magnitude is represented by how long the arrow is, okay? Pretty straightforward, pretty simple. A couple of things that you'll need to know in terms of anatomy. The back of the arrow, the part that does not have the point on it, is called the tail of the arrow. And the part that has the arrow, that is called the head of the arrow, or the head of the vector, okay? So not only are we going to look at vectors and see how great they are, but today our big goal is to add them. We're going to add vectors together. So adding vectors is pretty simple. It's kind of like adding numbers, but not only do you have magnitude, but you also have direction, and so we need to pay attention to that. So the thing that is important and we want to write down right now so that we know is that when we add vectors, okay, we always line them up, the arrows, head to tail. Okay. So you draw them as if it's kind of a path of motion, okay? So it's like a little map that you're following, okay? And when you add vectors, just like, you learned this when you were in elementary school, when you add two numbers, you get this thing called the sum, right? And if you subtract two numbers, you get this thing called the difference. When you add two vectors, you get something, and I can't remember if he said this in the video or not. Did he say what it was? When we add two vectors or no? Okay, well, I get to tell you then. Yay, I get to do the big reveal. Okay, when you add two vectors, the answer, the thing you come up with, is called the resultant, which is kind of a nice word, right? Because it tells you it's the result, okay? And the resultant vector, okay, is always drawn from the tail of the first vector to the head of the last. So I want you to write that down, put a box around it, put your glitter pens around it, whatever you need to do so you don't miss that that's it. You're going to say, I don't really know what that means, Miss Kay. And I'll say, I know, but we're going to do some problems in just a second, and then you will. Okay? But I want you to have it written down so that you understand what the process is going to be. As with most things in here, we're going to start with a pretty easy example. If you look at this one, you're like, well, duh. Then I don't want you to turn your brain off because it's going to get harder in just a minute. I promise. Okay? But I want to make sure that everybody is with us and that everybody can jump on board with us together, okay? So we're going to start this first one. We've got Gru. He's going to walk 15 meters east, then 10 meters west, and then 7 meters east. Why? I do not know, but that is the fact of what's happening. So we're going to go ahead and draw this. So we need to make sure that we know which way is north, south, east, and west. We're going to go ahead and use the cardinal directions just because it's pretty standard. Up here is north, east, south, and west, okay? If you want to set it up differently, that's fine, as long as you stay consistent and that it all follows, okay? You have to kind of keep it all together like that. So we're going to go ahead and draw those vectors. So if you don't have to write down the problem unless you really want to, but we're going to just draw the picture to show what's happening. So the first thing that happens is that he moves 15 meters east. So we'll give him a starting spot, and then we're going to draw a vector to the east that is 15 meters long. Does it literally have to be 15 meters long? No, you would need a very long piece of paper, right? Does it have to be 15 centimeters long? No. It doesn't have to be perfect, but we do want the arrows to be relatively, of relative size so they kind of match. So that first one's going to be 15 meters to the east, okay? And then usually I put them kind of right on top of each other, but this one's confusing since he goes back and forth and back and forth. So I'm just going to draw it down here. So he walked 15 meters east, and then he's going to go 10 meters west. Can you draw that vector? So you're going to start from here and go back. Is he going to go back all the way to his starting spot? Is he going to go past it? Or not quite to it? Not quite to it, right? So this first one was 15. The second one is 10 meters west. So we'll start here. And again, generally I draw these on top of each other, but I don't want to confuse us more. So I'm going to say 10 meters west. So it's kind of pacing back and forth. Do you see? Okay. So he goes here. This one needs to be about 2/3 the size of that one. I'm not going to get a ruler out and measure. Okay. I used to teach this where we had to get a ruler out and measure it all. That was painful and terrible. So I'm gonna allow you to avoid that pain. Okay. And then from here, what's going to happen? 7 meters east. Does he make it all the way back? Not quite. So I'm just going to extend this down a little bit. And say it goes like this. 7 meters back to the east. So I've put all of my vectors so that they go from head to tail. So I go from the tail here. I went all the way up to the head, and then I'm going to add this. The resultant vector, where does it go? You have it written down on your paper. Where does it go? From the... So you guys should all be able to see this. Do you see it written on your paper? Yeah, so I'm going to ask, and everybody's going to say it. Because, friends, when you say it out loud, it gets sunk into your brain just a little bit more. So let me ask again. Where does that resultant vector go? It goes from the... Bam! All right. Tail of the first to the head of the last. Let's do it. So the tail of the first, here it is. Tail of the first to the head of the last. Right there. Okay? So this is the resultant. And we need to know the direction and magnitude of the resultant vector. The resultant is sometimes known as like, where could he have walked instead of pacing back and forth? What's his displacement? How big is that resultant vector? What'd you get? 12 meters? For some of you, that's like, well, duh, why did we even draw this picture? That's a pretty simple problem. For some of you, like, wait, what in the world is going on? So we had plus 15 minus 10, so that puts them at a plus 5. Does that make sense? Plus 5, and then we're going to add 7 to that. That's where that plus 12 comes from. So the resultant vector is 12 meters, but that's only a magnitude. But remember that vectors have to have both magnitude and... I appreciate your participation. But you know what? Everybody knows this. I'm going to ask again. Vectors have both magnitude and... Direction. Yeah, they do. What is the direction? The resultant vector here has a direction of what? East. Yeah. So 12 meters east. That is the complete answer. How are we doing? Easy enough? All right, let's make it harder. Yay! Apparently George starts with a J. This is the thing that I've learned today. I don't know. I'm not well versed in all of this, so I just kind of am learning as I'm going here. All right, so George walked 4 meters north, 6 meters to the east, and finally 12 meters south. The question asks, what's his displacement? So the first thing we're going to do is to draw a picture. Does that make sense? So I'm going to let you go ahead and try that right now. You go ahead and try that and see how that goes. Okay? 3 vectors. North, then east, then south. Time is of the essence, my friends. I'm going to start to draw a picture too. You can compare with me. 4 meters north.
Exquisite.
It is nice to have somebody who's so positive as your table mate, right? Exquisite. 4 meters north. 6 meters east. Oh, you can't see my pretty picture. That's okay. I will unfreeze it so you can see the exquisite work that I've done so far. And then we've got 12 meters south. the first one? Yeah, I told you it's going to get a little harder, right? We just keep getting harder and harder and harder. All right, so I've got my 3 vectors drawn. Does your picture look kind of like mine? Sweet. All right, what do we need to do next? We need the displacement, so we need to find that. It starts with an R. Oh, that was kind of quiet. Let's try one more time. We need to find a resultant. Yes, thank you. It makes me so happy when you guys are all there, and I can hear your excitement. Excitement. Resultant goes from the what to the what? The bam. So it's going to go from that black dot where I'm starting all the way over here. Okay? Something like this. All right. This one's a little different. Just glancing at that, can you tell me how long that vector is? Probably not. I mean, maybe if you're really, I don't even know. Probably not is really the short version. Any ideas of how we could figure that out? How we could figure it out? Yeah.
The Pythagorean Theorem.
Yeah. We're going to use the Pythagorean Theorem. I'm going to be a little clever here because Pythagorean Theorem requires that you have a what kind of triangle? A right triangle. So let's make ourselves a right triangle. So friends, the game is that we always need to find a right triangle that the resultant is the hypotenuse. Yeah? The resultant is the hypotenuse. So let's go ahead and see if we can find that triangle. It looks like here is the hypotenuse of this triangle that looks like this. How are we doing? So if I'm going to use the fancy pants Pythagorean theorem, that means that I need to know the 2 legs of the triangle, right? Do y'all remember the Pythagorean theorem? It's been a few days. Well, what is it? A squared plus b squared equals c squared. Does it matter which ones of these are which? Can this be any of the sides? C has to be the hypotenuse, right? So this one over here has to be the one that is C. Do we know the lengths of A and B? Yeah? What are they? What is this one up here? That's 6, isn't it? Because it's parallel to the other one. So that's 6. So I'm going to just go ahead and write that down over here. This is really 6 meters here. So we'll call A 6 meters. And then talk to me about B. How long is this side, the vertical side of this triangle? 8. Where'd you get 8 from? I don't see any 8s written on this paper. 12 minus 4, right? Because you went up 4, then you went down 4, and then you went down another 8. And that's what really matters, is that down another 8. So that's going to be right here. That's going to be our 8 meters there. Okay? And so then you're going to get out your calculator, or if you see beautiful, nice 3, 4, 5 right triangles, you might see that right there. Either way, figure out what the hypotenuse is. Figure out the magnitude of that resultant vector. Go ahead and do that right now. See if you can figure it out. The resultant magnitude. What did you get for that length? 10? 10 meters. So I got 10 meters for my resultant. Yay for me. Is that a vector? Or is that a scalar? That's a scalar. A scalar is just a magnitude, right? I don't have any direction. I need direction, don't I? Yeah. Give me some direction. I need to know where George is. And I want to know exactly where he is. Southeast. I hear a lot of people saying southeast. I got to show you something, though. So if I draw my cardinal directions like this, and I tell you that George walked 4 meters north, 6 meters east, and 12 meters south. So let's say he just walked, and I need to find him. He's lost. Help me, help me, help me. I need to know exactly one place that he is. And if I know that he's 10 meters away from his starting place, southeast, how many different places could he be? A lot. Like technically, mathematically, an infinite number of places. I want to know exactly where he is. Exactly. Which means that I need to find a what? An angle. Okay, so here we go. Now, for some of you are like, no, like I don't want to do that because it's so scary. But I want you to take a deep breath with me. In, and let it out. Some of you freak out about this because you had a bad experience. Some of you loved it. Some of you don't even know what we're getting into. Either way, I'm going to walk you through it right now. You ready? Okay, so we need to find an angle. Here it is, friends. We're going to find this angle right here. It's theta. Have you met theta before? Theta is right there. It's one of the Greek letters. It's like, I don't know, 10 theta or something like that. Theta. T-H-E-T-A. Say it with me. Theta. Theta. It's a Greek letter. We say it theta. T-H-E-T-A. Okay, we want to find an angle. It's a right triangle. Because of that, we can use this beautiful stuff called trigonometry. Okay? And don't make that face at me. Don't make it at me because I will tell you I felt that way too when I was in your spot. I didn't have a great trig teacher. It was really hard. But I got your back. I'm not saying you don't. I'm sure that you guys all have great trig teachers, but sometimes it's hard the first time. I'm going to help you. You got it? You got to believe in me. You got to trust me, and you got to do this with me. Get out your equation sheet, friends. Bottom left-hand corner. It's right there. Put a little faith in me. You got this. It's there. Let's go. Let's do this, right? Now, I am aware that the bell is going to ring. Here's what I need you to know. For those of you that have heard this trig spiel before, you should be able to jump into this. If you have not, I don't want you to stress. I want you to start this homework. You can get the magnitudes for this homework even if you don't have the angles, okay? We'll get the angles tomorrow. Page 189, numbers 1, 2, and 3. All right? Have an awesome Monday, you guys. I will see you tomorrow.